So, ladies and gentlemen, thank you for watching my video. And before I start, I'd like to thank Professor Zhang for giving me this chance. So my name is Dinkai Zhang. Well, let's begin. So the title of our paper is Extraction of Medication Effect Relations in Twitter Data with Neural Embedding and Recurrent Neural Network. So a major component of pharmacovigilance is to continuously monitor and evaluate market drugs for safe use. And as we know, social media has become a popular platform for people to share their personal experiences, including those on medication effects. So because the wealth and the value of personal medication experiences, this source of data is becoming alternative for pharmacovigilance in order to augment the surveillance data. So there are some existing works have been done for the task. And first, the researchers use Twitter data as the data source to extract the information, but they mainly focused on entity relation recognition, like on relation extraction, which would help us to understand the medication effects. Also, there exist a number of methods for extracting related relations in biomedical field, including machine learning-based methods such as the dependency tree-based approaches and kernel-based methods. But these methods were developed mainly for precising formal writings of scientific literature. So here we should notice the characteristics of Twitter data. It's noisy with incorrect grammatical and spelling, with creative short text due to the limited space, and also it has ambulance from short tests. So the conversational methods for formal writing may fail when understanding the tweets. In identifying relations in Twitter posts pertaining to medication effects, we define the three types of relation between a medication and effect expression based on the CIDR database. The CIDR database contains information on marketed medicines and their recorded adverse drug reactions. Our relation types are the first is side effect, which is I's, and the indication means for beneficial relations, which is I, and no relation, which is N, which means neither side effect nor indication. Here are some examples of these three relations. You can see here. So here is the pipeline of our study. And you can see that after the initial processing of Twitter data, which is described in the data section, a corpus of tweets containing at least a medication and one or more effect expressions were generated. This corpus was annotated and later used by both baseline methods and the proposed neural embedding approach. Classification performance of each method was collected and evaluated. Finally, statistical analysis was conducted to confirm that the existence of any differences in classification performance between the baseline methods and the proposed method. And in the data section, collection of, here is the pipeline of how we collect our data and select the data we use in this paper. And first a collection of 53 million tweets related to 100 medications was gathered using a web crawler developed by our team in compliance with the Twitter.com access on policy. And pre-processing the 53 million rand tweets generated 12 million clean tweets, which are English only, non-duplication, and not retweets. Furthermore, the clean tweets were filtered with effects terms obtained from the CIDR database and their variations in consumer healthy vocabulary, which is CHV, yielding a corpus of 3.6 million tweets, which were used to infer the pairs of medication and effect based upon the relational similarity. Finally, 300 pairs were randomly selected, and the 9,516 tweets containing these pairs of medication effects were retrieved from the collection of 3.6 million tweets, which is finally what we used in this study. This random sampling was intended not to overwhelm our team with annotating the entire collection of 3.6 million tweets due to the time and the resource constraints. And so here is our methods. As I introduced in the previous slides, we compare the baseline methods and the proposed methods. The proposed neural embedding approach, which is word-to-vect. For the baseline methods, we have 4 methods, which are the TF-IDF plus SVM and Bagel words plus SVM, TF-IDF plus DNN, and Bagel words plus DNN. And the structure of DNN contains 5 hidden layers with 1,500 nodes in each layer. For the proposed neural embedding approach, which is word-to-vect, the output it's from a crop of 12 million unlabeled tweets, and the window size was 10. The output was fed with a long short-term neural network, which is the LSTM, and it contains 128 unit input layers with 3 units output layers to helping retain the semantics within the context of each tweet. In the statistical analysis section, both baseline and the proposed methods in this study were evaluated with the tenfold cross-validation, and the average value was calculated for each performance measure to confirm the existence of any differences of classification performance between the neural embedding methods and each baseline method. The Wilcoxon signed rank test performed on each pair of a baseline methods and the proposed approach for the same data partition. And the beauty of this test is that it doesn't have any assumption of the distribution of the data. The performance difference is considered in existing if the signed rank value is not more than the critical value of the given alpha and n for this study, which is 0.05 and the order of 10. So here is the results, and here's 2 tables of the results of our data. The top table lists the performance measures of each method for each class type of relations. And the first four methods are the baseline methods. And the last one is the neural embedding approach. As we can see, the neural embedding methods achieve the highest value in 5 out of 8 performance measures, whereas 2 baseline methods achieve the highest value in the remaining 3 methods, precision and recall on S-class and recall on N-class. In practical applications, we are more interested in whether a method can predict side effect relations and beneficial affection relations correctly, and the performance on N-class should not be a major concern. For accuracy and measure for all the classes together, our method achieved the best performance with the support of statistical confidence. As to the precision, our approach achieved mixed results. For the S-class, there is no statistical support to the differences between our proposed methods and any baseline methods. For the I-class, the proposed method performed better or identically well. And recall and F1 weighted also show their results. You can see from the table, and here I just escape this thing. So the results may be due to there are a number of observations of misclassification. For example, several tweets contain multiple medications and multiple effects. So finally, we conclude 2 points from our study. First is that the neural embedding method is a good candidate if a single method is for our task. And the second point conclusion is that the proposed method can help automate processing and analyzing the sheer amount of social media data to understand personal experience of medication effects, detecting potential unreported drug effects. Thank you.